Hello, Woodstock Science students. This is Mr. Brennan, and I just want to walk you through a little bit of some background ideas that go along with the notes that you are receiving. A good place to start is with the slide we had up the other day as we talked about the relationship between temperature and energy and mass and specific heat. And you'll recall that at first we had the specific heat in the numerator, and I realized how that was a mistake, and we wanted to make sure that was down here. So that should be the latest version of the equation that you have. But if you look at today's notes, you'll see that this has been rearranged. It's just a kind of an algebraic rearrangement. If we multiply both sides by C and M, we will get this equation right here. Q is equal to mc delta T. And you should see that on your notes here, right in the middle of this page, okay, when everything is defined here in terms of the units and such, okay? There's some additional reading, of course, and then some thoughts about power and power and slope down here, but we'll come back to that at another time. Today we want to head off in a slightly different direction. The direction we want to head in today is this, so if this is our relationship between energy and temperature with the mass and specific heat impacting that, what if we have multiple items being heated at the same time? It turns out to be a pretty simple adjustment in that each item has its own mc delta T term. So let's say, for example, that you had a glass marble that was inside some water, and the water, everything was put into a silver cup, and you were going to heat that up. Some of the energy would go into heating up the glass marble, and some of the energy would go into heating up the water, and some of the energy would go into heating up the silver cup. And you would just need to know the masses of each thing, and you would look up the specific heat of each material, excuse me. Here's the thing about the change in temperature. Unless we know something much more detailed about the problem, we can assume that the changes in temperature will be the same. That, for example, the marble, which is sitting in the water, has had a chance to come to equilibrium so that they start at the same initial temperature. And furthermore, that those two things have sat inside the silver cup long enough so that it is also at the same initial temperature. And when we heat up these items, if they are out of equilibrium at any moment, we're going to make the assumption that pretty quickly they'll get within equilibrium, and they'll all have the same final temperatures. So if they have the same initial and final temperatures, then of course the changes in temperature will be the same. That may not always be a perfect assumption about the world, but it's the one we're going to use, and it's not too far from the truth in many cases. Let's take a look at a particular problem. Here's a kind of classic problem. We've got a little bit of water in a glass cup, and we're just simply asking the question, how much energy will it take to increase the system from 23 degrees C, which is roughly room temperature, to 45 degrees C. So let's take a look at that. Okay, so we have two items in the system. We have got an MC and a delta T for water, and we've got an MC and a delta T for the glass, and we just need to insert what we know here. The 645 milliliters of water are 645 grams, which makes that 0.645 kilograms. We need to be in kilograms as we put in our masses. We look up the specific heat of water. That should be on a table that you are receiving today. So that turns out to be 4,180. It's a pretty big number. And then the change in temperature is the final minus the initial temperature, 45 minus 23. And then we repeat the same process for the glass. It's 400 grams, so 0.4 kilograms. 840, I'm actually doing this off the top of my head, so if that's wrong, you can correct that. But I think that's Correct. 840 is the value for the specific heat of glass, and the same change in temperature, 45 minus 23. And we go through for the water. It turns out to be close to 60,000 joules, and for the glass, it's only 7,000 joules. And you might say, well, that's the difference. There's more mass of water than there is for glass, and that's certainly true. But the biggest change, the biggest reason why these two numbers are so different from one another is this right here. The energy that it takes to change the temperature of water is much greater than the energy required to change the temperature of the glass. And so of the entire nearly 67,000 joules of energy needed, close to 60,000, or let's call it 90% of the energy goes into the water, and only a small amount goes into the heating up the glass. Okay. Now this may be the simplest version of this problem. We might know the energy and somehow try to estimate the mass of a cup or something like that, but that would just require algebra. We would have all of our terms in here, and something like this might be an unknown. We'd just be really careful with our algebra, multiply out and isolate our variables to get what we need. Okay. That should be enough for you to be successful this morning as you work on a practice set. We will come back to this soon, and hopefully you have a lot of success with this. Okay, great. Thanks.